Thanks, Romain and Yara, for inviting me virtually to Brazil. A pity that I couldn't come over. I've been in Brazil twice. I love your country. I love Brazil. And I'm still sorry about what happened in 2014, but okay, that's already 6-7 years past almost. So indeed, today I'm going to show you, it's a bit of a strange feeling just looking at a screen now, giving a seminar, but we have to get used to this, right? Entitled Unraveling the Properties of Topological Matter. And as Romain said, I'm working at the Radboud University in Nijmegen, and I'm working actually at the High Field Magnet Lab in Nijmegen. And the High Field Magnet Lab is this right building that you see on this picture. It has been joined in the past year by the Felix Laboratory, and the Felix Laboratory basically hosts intense terahertz radiation. The High Field Magnet Laboratory hosts high magnetic fields, and they are now joined together, not just the building, but also the instrumentation. So basically in the Netherlands, we are now able in Nijmegen to study materials, a quantum matter in high magnetic fields and even under terahertz radiation. A few words, because before I start with the talk, the High Field Magnet Lab in Nijmegen is part of the European Field Magnet Laboratory. I can maybe use my laser pointer. It's part of the European Magnetic Field Laboratory called EMFL. And in Europe, we have two static fields where you can basically go to 30, 35, 38 Tesla, stay there, do your experiments, and we can do this in Grenoble and Nijmegen. But we have also pulsed magnetic field facilities in Dresden and Toulouse, and you can go to magnetic fields up to almost 100 Tesla. But the disadvantage is that you can do this only for very short time scales. So the higher you go in field, the shorter the field will be at maximum. So you go from seconds to milliseconds to microseconds. This is our lab, our High Field Magnet Lab. We have in Nijmegen, we have 6 magnet cells. You can see here the magnets with the maximum field indicated. So at the moment, we have the highest magnetic field at 38 Tesla in 2 cells available, in cell 2 and in cell 4. And for experimental high magnetic field, where you need a little bit more space, I think Yara knows this perfectly. You can use other magnets, wide bore magnets with a 50 millimeter diameter, and there you can basically do also optics or complex experiments like thermal expansion and so on and so on. About the magnets, I will say something in a minute. The highest magnetic field we will soon have, not in 2017, but soon, is a combination of a bitter and a superconducting magnet, and this will be 45 Tesla in total. And if you look at the global picture of high magnetic fields research, we already have such a magnet, a hybrid magnet in Tallahassee in Florida in the United States. If you want to have more information about the lab, the High Field Lab and the Felix research facility, please go to these links, and since the video is recorded, you can do this also afterwards. One example of the magnets that we have, so our magnets are obviously not superconductors, right? Our magnets are bitter magnets, and the design comes from the High Field Lab in Tallahassee. So what you can see, you see copper silver plates, and they are put on top of each other, separated by an insulator, and fixed on so-called tie rods. And these tie rods and these copper silver plates, they form coils, and these coils are put into each other, connected with each other, put in such a housing, and then we will allow, for instance, for this magnet, 33 Tesla. And during operation, we're going to apply then a current of something like 40 kiloamps, which comes through these black big wires. I call them still wire. Yeah? And the water, the ionized water, of course, will be pumped through this magnet at the pressure of something like 30 bars. So in other words, we put something like a bath tube per second through such a magnet to take away the heat that, of course, is dissipated in the system during operation. So in other words, if you want to look at the energy, if we turn the high field magnet on, for instance, for your experiment, you roughly use as much electricity as a city of something like 30,000 inhabitants, just to give you an idea. Last but not least, we do, of course, HFML is a user facility. So if anybody from you has a good idea, he or she can write a proposal, contact us, and do a number of experiments on many, many materials. So you just see here a few types of experiments and research projects we are interested in. We basically have 3 groups: semiconductor nanostructures, strong liquid electron systems, and soft condensed matter. And we are also developing our magnet technology in-house. So with this, I want to switch back to the talk. I don't see any hands raised also. So if somebody has a question, I can't see it right now, but maybe it's just the best, Romain, to unmute him or herself and just shout, because I don't know if anyone has now any question.
Yes.
I don't see anything.
I think people can also switch on the micro and speak.
Exactly, I would prefer this. Exactly. So, okay, now let's go further to the science. And today, I want to present you results on topological matter. And I want to introduce the basics. So we all know different electronic phases of matter. For instance, insulators, semiconductors, and metals. And these materials, or these different phases or states of matter, can be characterized, for instance, by their electronic properties. Insulators do not conduct, metals conduct like crazy. Semiconductors, once conduct, once do not conduct, depending on the doping. And in condensed matter physics, we actually describe these materials by a band structure. And this band structure, dispersion relation energy, which relates the energy of the states to the momentum, you can see here for all three states. And the characteristic energy, at which, for instance, also you measure transport, tells you whether the material is an insulator or a metal. In a metal, the Fermi energy or the chemical potential is simply placed within a band. In a semiconductor, again, to emphasize it in terms of conductivity, doping can tune this material on and off. And semiconductors are basically the building block today for all our instrumentation devices, computers, smartphones, and so on and so on. So until the beginning of the 1980s, these states of matter were quite known, were characterized, until this gentleman, Klaus von Klitzing, did actually an experiment in high magnetic fields. So what he did, he studied a two-dimensional electron system, which you can, for instance, create if you create an interface of gallium arsenide and aluminium gallium arsenide. And this two-dimensional system is characterized that charge carriers only move in two dimensions. So, for instance, they move in the XY plane, but they are not allowed to move in the Z direction. So that means this two-dimensional system is confined to two dimensions. And by bringing this system into a high magnetic field, what he observed was that you see a longitudinal resistance Rx6 and a Hall resistance Rxy on the right side as a function of the magnetic field, that while the magnetoresistance is oscillating as a function of field, the Hall resistance, as we know from high school textbooks, is not linear anymore. The Hall resistance is quantized, and quantized in units of h/e squared. So if you convert the Hall resistivity to a conductivity, you will notice that this Hall conductivity is quantized in units of e² times an integer number. And this integer number is 1, 2, 3, 4, 5, 6, 7 for decreasing fields, but it is quantized in units of e². The picture that has been developed was that in such a quantum Hall system, this phenomenon can be described by so-called chiral edge states, which transport the current in a magnetic field, while the bulk interior of such a material is actually localized. And the number of edge states actually tells you the number of occupied channels, tells you the filling factor that you have in your system at a certain magnetic field. What was very interesting about this discovery was that this was not confined or specific to a certain material system. So any two-dimensional materials provided or given a sufficient high quality showed this effect. This effect was characterized by only natural constants, the charge and the Planck's constant. So it's a fundamental property of two-dimensional material systems. And more interestingly, as you can see in this picture here on top, these edge states are robust to disorder. And this effect has been awarded with the Nobel Prize, or Klaus von Klitzing has been awarded with the Nobel Prize in 1985. And actually 5 years ago, the General Nobel Prize on the concepts on topological phase transition and phases of matter, and the quantum Hall effect is one of them, has been awarded to these three gentlemen in 2016. And topology in terms of mathematics and physics, if you want to think about topological object, it's always counting the number of holes in a material, also called genus in mathematics. And my favorite topological object is actually a pretzel, since I'm from the south of Germany. And such a topological object would actually have 3 holes, so it would have a genus of 3. So this was the birth of topological matter, but this topological matter became even more ubiquitous by the discovery of topological insulators. So I have here a timeline from 2005 to roughly nowadays, and topological insulators have been theoretically predicted and discovered in 2005 and 2007 respectively. first in 2 dimensions, but later on bismuth selenide, bismuth telluride, so materials with nice thermodynamical properties or thermal properties. Then they've been realized also in 3-dimensional systems. And if you go along the timeline, after these topological insulators, also topological crystalline insulators and topological metals or semi-metals reached the scene. And intensive research has been done on these systems from 2012 on. And the system that I'm going to present you today, where we have done a lot of research, is actually a nodal line semi-metal. The differences between topological insulators and metals are the following. First of all, there are many common properties. So this topological matter or states actually occur in materials, let's say roughly at the bottom of the periodic table. So spin-orbit interaction has to play a role. The carriers behave like Dirac, Weyl, or other fermions. Geometrical phases are involved, and the band structure can be also characterized by so-called band inversion. So here are the examples. On the left side, you see a typical insulator described by the gap, which separates the conduction from the valence band. A topological insulator has a bulk band gap. However, it has surface states in between the conduction and valence band, while a 3-dimensional metal or semi-metal actually has a touching point exactly at the position of the Fermi energy in the ideal world. So you see already from the dispersion relation, you have both here on this right side for the Ti and also for the Dirac semi-metal, you don't have the Schrödinger equation that you can use to describe your particles in the system. You have to apply the Dirac equation. So topological insulators and semi-metals, they have actually different properties that you can measure, or you can detect their fingerprints in conventional experiments. The topological insulators have the opportunity or the property that they're insulating in the bulk of the material, while only their surface or edge is conducting in 2D. 3D, it's the surface. The metals, however, they are conducting both on the surface, but also within the bulk. But there are specific properties of these materials, again, which you can probe in various transport experiments, for instance, also in high magnetic fields. So in general, if I ask the question, very general, what are we actually looking for? So already in the 1940s, people have thought in band structures, what are the specific points, crossing points, that could give rise to specific, let's say, quasi-particles that reside within your material. So what we are looking at specific crossings in the band structure. And depending on the symmetry of these crossings, the particles, again, living or residing in these materials, they can be described by different quasi-particles. For instance, Weyl fermions or Dirac fermions, and so on and so on. The challenge experimentally is that often these materials do not have their Fermi energy near these crossing points. You rather have to bring your Fermi energy towards these crossing points, and then, of course, detecting the properties of the material. As I said, we can discuss the physics of fundamental quasi-particles, which we can't discuss or detect in high-energy physics, but we can do this in condensed matter physics. Topology always is robustness in material. So if you have states that are robust, like these edge states in the quantum Hall effect, they give also, there's no backscattering in these materials, and there's also a chance to find a very large carrier mobility in materials that is much higher, for instance, in conventional semiconductors. And one topic that I want to touch today at the very end, which is actually new, is trying to understand correlation effects in topological matter. For instance, if you look at superconductivity or magnetism in topological matter, since the underlying band structure is different compared to conventional materials, new phenomena may actually arise. But this is just the starting point of a new research area. Of course, there are many speculations about possible applications. I don't want to go into details here, but the overall idea is, of course, to create novel functionality, novel transistors, to go beyond the electron as a kind of controlled 0 and 1 in your system, but maybe you spin or other properties of these materials. So if you bring these materials or design materials or study new materials and find materials with these properties, and you bring this up to room temperature, of course, it could revolutionize our current devices that we all employ and love. So today I want to focus on topological semi-metals. So if you think about a fundamental definition of a semi-metal, you always say, hey, it's a material where you have an overlap between the conduction and the valence band. But depending again on the crossing, whether you have a 4-fold degenerate system or whether you have a 2-fold degenerate system. You can assign the quasi-particles living in these materials to either Dirac or Weyl fermions, or the materials I discussed today, where the nodal semi-metals, where basically conduction and the valence band, they touch each other not in a singular point in the Brimmer zone, but they touch each other along a closed line. The techniques to unravel material properties of topological matter in general, there are many of them. You can do angular resolved photoemission spectroscopy, or in simple words, the photo effect, to discuss or discover surface and exotic bulk states, or the other way around. You can look at magnetoresistance, look at the properties like carrier density, mobility, isotropy or anisotropy. You can look at quantum oscillations, which is the topic actually of today. You can also do optics, for instance, study optical conductivity and look at the optical conductivity as a function of the frequency or wave number. And from there, you will have ideas about the dispersion relation and the dimensionality of the material. You could also do this, for instance, looking at STM, but today the focus is on the quantum oscillation technique, especially, of course, in high magnetic fields. So my collaborators for this project here, which I'm going to present today, we call this loop-the-loop electron style. You will see later why we call it like this, are from chemistry department, from Princeton University, from the Max Planck Institute, from our institute at the Radboud University, Denmark, but also Bristol. And in the bottom part of this page, you can also see my current and former team members who contributed to this work. So today I'm going to first introduce the nodal semi-metals. Why are these materials so special and why are we interested in these materials? Then I will show you how we can measure and analyze these quantum oscillations, a very fundamental and powerful tool to look at the Fermi surface of these materials. Then I will discuss with you a few measurements, and then especially loop-the-loop, I will show you a phenomenon called in-magnetic breakdown, which is actually a kind of tunneling phenomenon in momentum space. And later on at the end, I will give you an outlook what we're gonna do in the coming years if time allows. So why are we interested in nodal semi-metals and why specifically in this type of materials? The first point is these materials are ideal topological semi-metals. So if you look at your spaghetti plots of any material, if you go around in literature or just in the internet, the point is what you see, and if you just look at the central part, these materials do only have linear crossings around the Fermi energy. So there's no other parabolic bands in the vicinity or at the Fermi energy that could basically obscure phenomena that are related to topology. So you have isolated linear bands, which is the dream for every experimentalist to study and to look at topological matter. The second thing is, in these particular materials, nodal semi-metals, it has been predicted that topology coexists with ordered states. So basically correlated states, emergent states of matter, such as charge density waves, magnetism, or superconductivity. Third, in these materials, the specific Fermi surface, which I'm going to present you in detail later, allows for observations of quasi-particle tunneling in momentum space and also interferometry. And last but not least, of course, what we try to do if we start from zirconium silicon sulfide, we want to do material engineering together with our solid-state chemists to try to look for the textbook material to understand or to measure, to identify either one or several of these properties that have also been mentioned in theory. So this is our task and, of course, also a challenge. So let's look at the band structure. I don't want to say too many details here. The only thing that I want to say is that this zirconium silicon sulfide is just as a silicon square net that you can see that is sandwiched between layers of zirconium and sulfide. And these materials are grown by Leslie Shope now at Princeton University by iodine vapor transport. These materials are relatively easy to handle for us, so they're not sensitive to air. They're not toxic, so in terms of material preparation, we don't have to make that much effort. What is interesting for us is, again, the band structure. And I highlight it here again on this box at the right side on top. In this range, you have only linear bands. I should have shifted a bit down maybe. But again, you can study the properties of Dirac matter of this kind of nodal semi-metals in high magnetic fields. And what you detect in transport or in the Haas-Phenolphthalein experiments is you detect everything that is at the Fermi energy. In transport and quantum oscillations, I repeat, you detect everything, all the states, all the carriers that are residing at the Fermi energy. For the theoreticians in the room, maybe you have noticed that this dispersion relation is nevertheless gapped. This is due to spin orbit. An example for calculation without spin orbit you see at the bottom left, where you see that these linearly dispersive bands exist in a wide range of energies. And for the very experts in the audience that they know about band structure, the illustration of where the nodal line is actually is this orange ring. So if you go in your band structure, for instance, from gamma to M, which is here, or from X to gamma, you will see the bands, and in between you can detect this nodal line, or this nodal line is presented in the band structure, which you can see on the top left in this kind of closed line, this red line, in the simple representation of this material. So now let's look a bit in more detail at the Fermi surface of this material. The Fermi surface exactly at energy equals 0. So what you will see, you see the high symmetry points here at the bottom of your Brillouin zone, and you see the high symmetry points also indicated in this three-dimensional representation of your Brillouin zone. And if we go now step by step through this Fermi surface and we focus just on the set R A plane on top, so in the band structure set R and A, if you go from set to R, you will see that the Fermi energy cuts here the conduction band, which means it's an electron pocket. And if we cross the Fermi energy, if you go from the set to the R point, you will see here at the edge is this blue pocket. And this blue pocket, since the Fermi energy is in the valence band, it is a hole pocket. So like this, you can identify all these pockets. So those other two pockets that are just in the gamma plane. But for this presentation, the entire physics and the entire story that I'm going to present only takes place here in this set RA plane. And this band structure calculation is simple. It's not that simple, but it's a density functional theory calculation using the package Wien 2K that you can get or buy at the website of the University of Vienna. So if we start to engineer these materials, I just show you one example. So let's just replace the zirconium by the hafnium. You will see the band structure looks more or less the same. Well, the gaps are a bit larger, but you see in that case another band pops in here right at the gamma point, which again will try or will obscure the observation of the linear bands that are sitting here exactly at the Fermi energy. Okay. So again, why are these materials so interested? There are already in the 2016 and 17 a few ideas that the point is that if you approach this nodal line in such a material, so if you tune the Fermi energy towards this nodal line, you will have a weaker screening of the Coulomb interaction compared to conventional metals. We know that in conventional metals, a large number of carriers needs to be present, and only a large number of carriers allows you to observe, for instance, superconductivity, so electron correlations, and for instance, superconductivity. But in this system, the phenomenon is a bit opposite, because if I decrease my Fermi energy, I actually decrease the number of carriers, and then I should theoretically observe this kind of order in the system. And I should see this, of course, in different experiments that I can conduct. But before we all do this, we have to really calculate and understand our Fermi surface, our charge carrier properties, and then start tuning it. There are first experimental evidences that indeed correlation effects sit in these materials. One is our own experiment we did in 2018. Where we saw an enhancement of the quasi-particle mass with field, which points to correlation effect, but also surface-induced superconductivity has been already observed in this material. So now let's look at a technique that we're going to actually use to unravel the Fermi surface of this material and identify possible correlation effects. So we're going to use and start with a textbook lambda quantization of a charged particle, an electron, in a magnetic field. What you know from university, we will observe an energy quantization, which gives you in a three-dimensional system the Landau tubes, the lambda quantization. So the energy is quantized in h bar omega times n plus 1/2. So if you put your system into a magnetic field, your Landau tubes actually, your Landau levels or Landau bands, they form this kind of Landau cylinders. And by increasing the magnetic fields, one by one of these Landau tubes will subsequently leave the Fermi energy, and this gives rise to oscillations in the density of states, which are periodic in 1 over the magnetic field. And this gives rise to quantum oscillations, for instance, in the resistance, but more generally in any thermodynamic quantity as a function of magnetic field. So this quantum oscillation is a normalized resistance as a function of 1 over B, and this gives rise to these quantum oscillations. And these quantum oscillations occur, of course, in magnetic fields, but also in sufficiently clean samples, right? If your density of states, if you start to split it into different, let's say, Gaussian Landau bands or Landau levels, you have to, of course, have a sufficiently clean system that you have a separation in your system. And of course, you need to make sure that your field is high enough to overcome also the thermal energy. And then you have the conditions to observe quantum oscillatory phenomena in quantum matter. So,
excuse me.
Yes.
I didn't understand. What is quantized in these oscillations?
The oscillations are not quantized. What is quantized is, so what you do technically is you take an electron into a magnetic field. You take the Schrödinger equation, you solve it, and what you will end up with the so-called Landau levels or Landau bands. Mm-hmm. So what is quantized is the density of states in units of the magnetic fields. And the consequence of a quantized density of states is the observation of quantum oscillations in any thermodynamic quantity or in the magnetic in resistance. Yeah, so it's the quantized density of states that gives rise to the observation of 1 over B periodic quantum oscillations.
Okay, because the period of oscillations is not quantized, or
no, the periodicity is one frequency that we will now extract, but the quantity, the resistance, and any thermodynamic measurements, so the Haas Phenolphthalein, thermal conductivity, magnetostriction, you observe this quantized or these quantum oscillations because the density of states is quantized in a magnetic field.
Okay, thank you.
Okay. So now the question is, what can we do with these quantum oscillations? The answer is, in short, we can extract many fundamental properties. So what you see here is an example of, again, this normalized resistance, this time as a function of magnetic field. And you can describe such an oscillatory behavior by such a term. So you have a sine term, which you can imagine is the oscillatory component of this picture. And in this oscillatory component, you will see the frequency. So we can extract the frequency, for instance, by making a fast Fourier transform to the signal. And for this particular signal, the frequency would be 193 Tesla. With this frequency, we can use the so-called Onsager relation to extract the extremal area of a Fermi surface. So that means we know the area of our Fermi surface and can identify the specific pocket in our Fermi surface that you have just seen from zirconium silicon sulfide. I will come back to this later in a few minutes. Next, what we can do, we can measure this resistance as a function of field for different temperatures, what you see here. And from the damping of these quantum oscillations, we can extract the cyclotron mass of the electron, of the hole, or in general, of the quasi-particle residing on our Fermi surface. And moreover, we can have access, by looking at this envelope of these quantum oscillations, at the mean free path, the quantum mobility, or a so-called Dingle temperature of the system. So these are the fundamentals of quantum oscillation measurements. And now the question is, of course, hey, this Fermi surface is much more complex. So there are always many extremal orbits and, of course, different parts of the Fermi surface, which we could identify by using this quantum oscillation technique. And I have a simple example. I have such a peanut, since I'm from the Netherlands, I'm working in the Netherlands. Imagine you have a Fermi surface that looks like this. And if we now apply the magnetic field, for instance, in the blue direction, what you know, I think, from solid state physics, that an extremal area can be formed. The particle will go around this extremal area. And this extremal area, when the electron goes around, gives rise to these quantum oscillations with a specific frequency. So the frequency of these specific quantum oscillations, in this case 500 Tesla, is gives you access to the area of this peanut here, which is then a certain number in k-space. So the frequency tells you about the area in momentum space. If you apply the magnetic field along the peanut, you see there are 3 extremal orbits in our Fermi surface, each giving rise to a certain periodicity, because the frequency is proportional to the area that is enclosed by the particle. So what we see is, we see a frequency related to pocket 1 or 2. They have both the same area. And I see a frequency for number 3, which is a smaller area. And a smaller area always means a smaller frequency. But of course, if I apply the field in this direction, I will see 2 frequencies, so they're just superimposed, giving rise to this frequency here at the bottom, the combination of frequencies. And if I now tilt my peanut in a magnetic field, I change my extremal orbits, and by changing my extremal orbits, I can directly map the Fermi surface of this peanut. So if you have such a Fermi surface in material, you measure this in a material, and you rotate the sample with respect to the magnetic field, you can exactly determine that indeed the shape of the Fermi surface looks like a peanut. And now let me show you the real results. And these real results on real samples we measure, for instance, using the so-called Haas Phenolphthalein oscillations. So we take a sample, that's zirconium silicon sulfide, we glue this on a copper beryllium cantilever, then we take this copper beryllium cantilever, we screw it on top of an insulator, that at the end you have a capacitor with the cantilever as top plate and a fixed plate here at the bottom. And on top is the sample. And if we now bring this into a magnetic field, we are able to measure a torque. So the magnetization of such a sample will oscillate as a function of magnetic fields. And if this material oscillate, it will change the capacitance that we can measure, for instance, using a high-resolution capacitance bridge. In transport, the story is easier. You take your sample, you glue it on, for instance, an insulator, quartz glass plate. You put electrical contacts, that's just using silver paste here. You send a current along the length of the sample, and you measure longitudinal and Hall resistance along or perpendicular to the current flow of the sample. So now let's look at typical measurements of zirconium silicon sulfide. So our first measurement is a transport experiment. So you see the resistance, the longitudinal resistance, in units of milliohm as a function of magnetic field up to 33 Tesla. And what you will see, you see that the resistance overall increases as a function of magnetic field, and superimposed on this magnetic resistance are quantum oscillations. But if you compare to the quantum oscillation that I have shown you so far, you realize that this pattern is quite complex. So there are many, many frequencies in this oscillatory component of the magnetic resistance. And these many, many frequencies, they correspond then to certain pockets of the Fermi surface, which I'm going to show you on the next slides. Moreover, at very, very high magnetic field, you suddenly see very, very, very fast oscillations. And what I have said before and what we learned is that the frequency of the oscillation is always proportional to the extremal area in momentum space. So I will come back to this in a few minutes. Here are the same measurements, but this time in torque. The same material, zirconium silicon sulfide. That's just to illustrate you. So here you see the torque in arbitrary units as a function of fields for different temperatures. And if you look here, 4.2, 8, 15, 30 Kelvin, you see how fast these quantum oscillations are damped. If we moreover look at the lowest temperature, the 0.34 Kelvin, typical helium-3 measurement, you will see that there are very, very fast oscillations already visible at very, very low magnetic fields. And again, when we now discuss the Fermi surface in detail, this corresponds, large frequencies correspond to large area in momentum space. Okay, now let's start to analyze our zirconium silicon sulfide measurements and try to identify the pockets in the Fermi surface. So this is the Fermi surface again, here on the top right, calculated using DFT by this gentleman, Tony Carrington from Bristol. And what you see in this Fermi surface, everything that is green is electron, everything that is blue is hole pocket. And you see different Greek letters here, beta, delta, gamma, alpha. What you also see on the right side, you see a cut. One cut is in the ZRA plane. So this top cut is just a cut here on top of my three-dimensional representation of the Fermi surface. The other cut, M gamma X, is a two-dimensional cut in the center of the Primor zone. And now I'm going to show you the measurements. So this is a typical fast Fourier transform analysis from the signal that I have just shown you at the lowest temperature on the previous slide. So we take this signal, we make a fast Fourier transform, and what we get is we see many, many, many spikes in this signal.
Excuse me, sir.
Yeah.
Is this is experimentally or you are doing?
That's experimental data. Yeah, that's all experimental data. So this is the fast Fourier transform from the measurement I have shown you one slide earlier. So it's this curve that we measured. We made a fast Fourier transform.
Okay.
Yeah. And now what I said before is we have now to identify, these are all different extremal orbits. We have to identify these orbits now in the Fermi surface. So for instance, what I said again, I repeated 10 times already. The area of such a pocket corresponds to the frequency. So the larger the area, so beta is larger than alpha, the larger the frequency. And indeed, those two, the alpha at 240 and the beta at 420, you can see marked here. But there are also many other peaks. You see at low frequencies, the delta 1, delta 2, gamma 1, gamma 2. Those frequencies correspond to tiny orbits, the tiny area of the gamma X M plane. But there are also other frequencies here in this fast Fourier transform spectrum. For instance, at 600, at 300, or at 180. And those frequencies, they originate due to magnetic breakdown in these materials. And I'm going to discuss this with you in roughly 4 or 5 minutes. But let's finalize first the characterization of the Fermi surface in zirconium silicon sulfide. You could say, okay, now for this particular spectrum, we have applied the magnetic field perpendicular to the Fermi surface. But what you can also do, and what I said when we discussed the peanut, that I have to rotate my sample with respect to the magnetic field to basically directly determine or to identify the pocket, then we would have to do an angle dependence. And that's a measurement one of my master students did within 1 month. And what he did is he measured the quantum oscillations for one certain magnetic field, and then he always changed the angle between the magnetic field and the sample by 2 degrees. And then he got this beautiful picture here. So these are all fast Fourier transforms put on top of each other. So each fast Fourier transform corresponds to one angle, rotating the sample from first be applied perpendicular to be in plane. And what you see at the bottom, you also see these open black dots corresponds to the maxima that you see in this top left plot. That's the experiment. The straight lines, they correspond to the density functional theory calculations. Green for electron pockets, blue for hole pockets. And what you see is that some pockets, for instance, this alpha pocket, theory perfectly fits the experiment. But if you look at a pocket, this beta pocket, this green pocket here in the Fermi surface, you see there's quite a very, very strong discrepancy in the magnetic field. So the frequency here is 420 Tesla, and experimentally 420, theoretically, it's something around 515. So there's a big difference, and this difference we can assign likely to correlation effects for a certain pocket in the Fermi surface of this material. More interestingly is that this Fermi surface, these quantum oscillations, you can measure in torque. That's the top curve. We can do the same measurement also in transport. And if you do then the fast Fourier transform, you will get this spectrum at the bottom. So what you can see is there are some similarities, but also some differences. And in particular, there's a strange difference because this beta pocket we see in the Haas Phenolphthalein is absent in the Shubnikov-de Haas oscillations. So if you measure a thermodynamic quantity like the Haas Phenolphthalein, you see this pocket. If you measure resistance, this pocket is absent. So these are some second-order effects, which I'm going to skip now in view of time. But just to illustrate you that if you use different quantum oscillatory techniques, you can unravel also details of the Fermi surface, like hotspots, vortex corrections, and so on, that will help us to identify the fundamental properties of such materials. So I want to go one step further. I want to skip this slide. And I want to show you now quantum tunneling in momentum space. I'm pretty sure you have heard already in your courses, fundamental courses, when you were discussing graphene, you were discussing the phenomenon of Klein tunneling. And Klein tunneling in graphene was, right, that you are in real space, that electrons can tunnel in the so-called puddles in graphene, and if you have n puddles and p puddles, so electrons and holes, they tunnel through the barrier, and this gives rise to conduction in graphene. So if the barrier is infinitively high, you have perfect tunneling, and this occurs for these Dirac particles in graphene, which is of course completely different to conventional tunneling, where the amplitude strongly decays if you hit the barrier, if a quasi-particle hit the barrier. So what about magnetic breakdown? Magnetic breakdown is a phenomenon that occurs in high magnetic fields. Suppose on the left side you have two pockets, two electron pockets, so the carrier travels counterclockwise on these pockets. And these pockets are separated by a very tiny delta k in momentum space. So if you increase the field, there is above a certain field a probability that the particle tunnels from one pocket to the other pocket. So in other words, the particle will go from here to there and then enclose both orbits, which you would see as a sum of the frequency in your fast Fourier transform spectrum. If you have adjacent pockets, which is an electron and a hole pocket, so in a hole pocket the carriers go in the other direction, then you would see this as a difference in your frequency in your system. And this electron-electron tunneling, or magnetic breakdown of electron-electron, is a very familiar phenomenon in organic metallic systems since many, many years. However, this electron-hole tunneling, this hasn't been observed until we studied these materials. And I'm going to show you now what a result of such an electron-hole tunneling is. So now take a material that's called hafnium silicon sulfide. That's a sister compound of zirconium silicon sulfide. What you see is, you see again an alpha pocket, which is this blue pocket. So here I plot again the fast Fourier transform as a function of frequency. And you see the green pocket, which was our electron pocket. And if I now make a fast Fourier transform up to very high magnetic fields, I see the alpha pocket, I see an harmonic of an alpha pocket, and I see a beta pocket. But interestingly, I also see a pocket which corresponds exactly to the difference of the beta minus the alpha pocket. So in other words, if I take my cursor, my laser pointer, the electron makes an orbit that looks like an 8. It traverses the electron pocket clockwise, the whole pocket counterclockwise, and then traverses the electron pocket again counterclockwise. Now you can ask me, okay, high magnetic fields, and I said, there's a probability that you observe this orbit. So let's do the following. I look at the data and measure only from 5 to 10 Tesla and from 5 to 18 Tesla. And if you look at this fast Fourier transform as a function of frequency at low magnetic fields, you see that this beta minus alpha orbit is absent. So you do not observe this pocket anymore. So you need high magnetic fields. And above a threshold magnetic field, you can see momentum space tunneling in this material, so zirconium silicon sulfide and the entire family. And of course, there's a certain gap in momentum space. These pockets don't touch each other. If they were touching each other, this would be the Klein tunneling in momentum space. In zirconium silicon sulfide, this magnetic breakdown looks much, much, much more complex. So I don't want to spend too much time on it. I rather want to give you an idea of what we're going to continue with these materials, further on. So here you see a fast Fourier transform of the same signal of zirconium silicon sulfide, and you see this is much more complex. So again, we see a frequency which is beta minus alpha, which corresponds to this particular orbit. But if you want to understand all these other peaks that you see here, you really have to start counting and making orbits. And I just want to show you one other example. Let's focus on this huge peak at 600 Tesla. And the 600 Tesla is 2 times beta, 2 times 420 minus alpha 240. And you can make such an extremal orbit if you look into this part here, where your electron transverses an electron pocket, goes around an alpha pocket, goes around an electron pocket, and comes back. So the electron has to tunnel 4 times to realize an orbit that includes 2 beta pockets and 1 alpha pocket. And all the other combinations you can also create with different types of orbits in the specific Fermi surface. Moreover, if you go to very high magnetic fields, I'm going to skip these slides, you can have another phenomenon. You see now orbits that are in the range from 7.5 to 9 kilotesla. So remember what I told you. I told you if the frequency is large, the extremal area in momentum space must be large. So how can I observe? Why do I observe these very high frequency oscillations in this material? Well, these electrons have to, these quasi-particles have to surround, circumvent, or transverse a large area in momentum space. And you see here many opportunities or possibilities how this works. So for instance, if you look at this figure here, the electrons goes around the entire Fermi surface of zirconium silicon sulfide in the ZRA plane. And it can, for instance, include exclude 1 alpha pocket. It can exclude 2 alpha pockets, 3 alpha pockets, 4 alpha pockets, and so on. And that's exactly what we see here. This peak here is our A plus for beta, and subsequently, by excluding 1 whole pocket, we get all the side peaks on the left side. On the right side, we would have to include or double the area, so this is a bit more complex. We can identify these pockets by doing a so-called temperature dependence, and we can extract the carrier mass from these temperature-dependent experiments. And by extracting the carrier mass, we can assign each of these frequencies, or by extracting the mass, we can assign each orbit to a certain combination of alpha and beta pockets that surround the entire Fermi surface of zirconium silicon sulfide. So this I'm also going to skip due to time issues, but I want to show you at the very end. First, I want to conclude. So what we have done so far on this zirconium silicon sulfide, we have identified all the pockets and the entire Fermi surface, which is quite rare for a complex topological material. This is quite challenging because A, the Fermi surface is extremely complex, and B, not all the time you are able to actually use quantum oscillation measurements to really determine or identify all the pockets in such a Fermi surface. Then what we have done is we see indications for correlation effects because we see strong deviations from one orbit compared to DFT. And as you may know, density functional theory is based on the single particle picture. It does not include, to the first order, correlation effects. Then we have observed the beauty of magnetic breakdown or Klein tunneling in momentum space, but this time between electron and hole pockets. And last but not least, and that's what I show you in the last 3, 4, 5 minutes, we are now ready to take this material, tune it, and search for possible correlation effects. I want to motivate this, and actually by asking the question, if you think about the catalog of all materials that we know, and there are a lot of databases, right, where you can identify, one is given here, how many materials do you think are actually topological? Do have some features, some topological features in their band structure? Is anyone brave, unmutes him or herself and says a number? What's the percentage of topological materials we know? Any guess? 50%, 80%, 10%, 1%? No idea?
I think it depends as its name. It depends on the on its shape. So I don't know, is it depends on the kind of material or
band structure? It's pure band structure. It depends, for instance, on crossings and symmetries in your Brimmer zone. It's pure band structure.
So can we change? Is it possible that band structure change with the geometry, with the topology of a system?
Yes, yes. But if you just take all materials at ambient conditions, and you look at this paper here from 2019, they have identified that 27% of all materials in nature are actually topological. And this is so far completely unexplored territory. So people have worked on topological systems, trying to understand Fermi surface, low dissipation transport, surface states, bulk states, and so on. But people haven't asked themselves yet what actually happens if many body effects exist in topological matter. Or, for instance, what happens if topology is present in correlated materials? How do my fundamental properties change in terms of pairing mechanism, in terms of symmetry, and so on, and so on, and so on? And that's a new project that we have started last year in the Netherlands. We have, in a big consortium, we have received a big grant where we try to investigate topology in correlated matter or correlation effects in topological matter. And I want to show you one final example by, for instance, tuning correlation effects in topological matter. So we have seen this in zirconium silicon sulfide, that indeed, if you take a bulk material of zirconium silicon sulfide, you can see correlation effects in this material. And what we want to do now is we want to use all the tuning techniques that we have. So gating, applying hydrostatic pressure, applying strain, high magnetic fields, and underlight to try to tune these material properties. So for instance, what you can do, you can apply strain. Use the technique of dilatometry. Dilatometry is a unidirectional measurement where you can measure along a certain crystal axis under strain and measure the thermal expansion or magnetorestriction in these materials. We can use a so-called strain cell, where if you look carefully in this picture, clamp a material in between two piezoelectric stacks, and then we can push the material together, pull on it, and measure the effects by pulling or pushing along a certain crystal axis. For instance, change in the magnetoresistance, change in the frequency of the quantum oscillations. And last but not least, of course, we can use gating. We can use electrostatic, but most importantly, ionic liquid gating. Ionic liquid gating is also electrostatic, but it gives you the possibility to apply much, much, much larger gate voltages to tune the Fermi energy in these materials. And of course, all this we're going to do in magnetic fields. And the ultimate aim is, of course, in this simple liquid to create a device based on these nodal and semi-metals that we can tune correlation and or topology on or off. And with this and a false color image of one of the backside of our magnet, I thank you for your attention. If you have any questions, ask them now or feel free to contact me.
Thank you very much for the very nice presentation. Are there questions?
Steffen,
yeah.
Thank you for a very beautiful talk. So just it may be it's kind of related to your experiment. So when you were showing the different paths for tunneling, so you're changing there globally the magnetic field, right? But in principle, can you select those tunneling paths by doing some experimental tweaking by increase one of those signals there regarding to the others? Like, I don't know if I'm clear enough with my question. So
I think what you want to change, you want to switch on or off these tunneling paths, right?
Yeah, so to enhance one much more than the other, just to select one of those paths.
That is experimentally simply not possible, because suppose the Fermi surface is quite symmetric. So if I change the distance between pockets at one edge, I will automatically change the distance also on another edge, right? So if I apply strain, for instance, I will push the whole Fermi surface apart. So the tunneling gap will become larger. And then, of course, the dominant ones might persist and the less dominant one may disappear. But I cannot turn on one and the other one off because I have to tune, at least if I apply hydrostatic pressure, I push on all axes, right? If I use strain, I can pull or push on one axis.
Oh, I see. I see.
So I can change the amplitude, the probability, but it will be always in a kind of symmetric way because I can't tune one part and keep the other part fixed. That's impossible.
I see. I see. Thank you.
Steffen, if I may return to the problem of the oscillations. So to understand, when you say you have a you get a discrete density of states, so it means basically you are emulating a kind of two-level system and doing some analog of Rabi oscillations. Is it the proper idea, or
not really? It is a kind of the best is, let me see, I think I should still have a simulation. So the point is, when you have a simple system, while I'm talking, I try to find a video that I can maybe show you. So the point is, if you have a simple Fermi surface which is just spherical, so you have a three-dimensional electron gas. Okay. And what you want to do is now you apply a magnetic field to this three-dimensional Fermi surface, a football, for instance. Yeah. I'm just trying to open my file now. Okay. And the question is now, what happens if I apply a magnetic field? So I will now try to share my screen again. And where is it? And see if I can show you what exactly happens. Because what has happened due to the Landau quantization, the states residing on this three-dimensional Fermi surface, they will break apart into cylinders. So I will now try to do this entire screen. I think just a Landau tube. So, and now I start my video. Can you see a Fermi sphere?
We cannot see your screen yet.
Okay,
since
then
okay, now it's coming.
Now it's coming. Now it's coming. Okay. And so this is the three-dimensional Fermi surface, Kx, Ky, Kz. And if I now apply a magnetic field, you see that these states, they all condense on these Landau tubes with increasing magnetic field. And by increasing the magnetic field, I push one Landau tube by Landau tube out of this Fermi surface. And this gives rise to this 1/b periodic oscillations, or the oscillation density of states. That's the overall picture. I hope this video illustrated it. Yeah. Okay.
Then, okay, so when you mentioned that there are 27% of the materials which have topological surfaces, so the question would rather be, why didn't we see more of these nice effects if these are so common? Material? Is it because you need a very strong magnetic field and specific conditions, or
yeah,
you are saying
I thank you so much for this question, because the precise point is people are doing research on many materials, but the problem is when you want to see topological materials, you need to have these isolated bands. You have to have, like in graphene, linear dispersive bands. But if I take materials like bismuth selenide for the surface states, it was mostly bulk. If I take natrium-3 bismuth, tantalum phosphide, niobium arsenide, all these typical materials that are topological, and if you look at the Fermi energy, so you see many bands that obscure the effects of topology. And also if you measure optics, suppose you measure optical conductivity, you excite between different levels, but if you excite between these different levels that are both linear dispersive and quadratic dispersive bands, you will measure both. So if you look at your sigma, at your optical conductivity and the proportionalities, you can't distinguish whether you have a linear dispersion or a quadratic, or whether you are 2D or whether you are 3D. So it mixes all up. So the key for experimentalists, I think, is to identify materials and then tune it. So what we are mostly doing now is to tune it. So either by doping to bring the Fermi level to isolated points where only linear dispersive bands are present. That's the key for experimentalists.
Okay, so you have to isolate
Yes, that is the underlying question, I think, for all experimentalists working in this area, not doing ARPES, of course. In ARPES, they see everything. ARPES probes occupied states, and you can distinguish between linear dispersive states and quadratic dispersive states. If you do spin ARPES, you can even extract spin.